Hello again. Welcome back to another exciting edition of Physical Chemistry. This is topic number 4, which is about phase transitions of pure substances. Okay. So first we'll start with the first section about phase diagrams. Only 2 sections, so this will be a fairly short chapter, but that's okay. That just means it's going to have a little bit of break between the first exam, which is kind of a lot going on, and then the last exam, which also have a lot going on. But this exam will be a little bit easier. All right. Now, when it comes to phase diagrams, we need a few definitions so that we're all speaking about the same thing. All right. First, a phase, as it says, is a form of matter that is uniform through its chemical and physical composition. All right. Uniform in chemical and physical composition. Key thing being uniform here. Oops, go back. Uniform. There we go. Now, each phase is going to have a chemical potential, mu. All right, so they're talking about chemical potential a lot during this chapter, and I'll talk about it more in other chapters that follow. All right, this chemical potential is just a different word for the molar Gibbs energy, right? The G sub M. All right, same thing. It's just mu chemical potential instead of Gibbs energy. That's all it means. All right. If two phases are in equilibrium, right, then the chemical potential of each phase are equal. All right, so if we have two phases, let's say one is alpha and one is beta, then what we're saying is that mu of alpha is equal to mu of beta, right? Or in other words, delta G between the two phases is going to be 0, right? The difference, and this is again, this mu is plain old G. The difference in the G's would be 0 because they'd be equal to each other, right? Keep this in mind very much. This particular thing is going to be a fact is going to be very important throughout the entire chapter. Okay, so keep that in mind. If we're at equilibrium, mu of one has to equal mu of the other. All right, so as it says here, when two more phases are in equilibrium, like say we have vapor on top and we have liquid on bottom, right? If they are in equilibrium, they have to have the same value of mu. Right? They have to have the same value of mu. Now, what we see in the next section, section 4b, we'll see how mu changes with all these different conditions, basically, right? But when we put all this sort of data together, right, what we can generate from this is a phase diagram, something like this, where we have pressure and where we have temperature. And we are writing the boundaries here of where, like, on here, honestly, here it is, right? We are looking, this is a whole graph of mu, basically. It's basically a big graph of mu, right? As it changes with pressure and temperature, right? So if we're in the solid phase, right in the middle of it, then mu of the solid is the lowest number, like literally the lowest number, right? Because again, mu is going to be Gibbs free energy. We're always going to go towards the most negative number, right? The minimum molar Gibbs energy, right? Over here at this pressure and temperature, right? The liquid has the lowest, and down here, the vapor has the lowest, right? And then what we see in the middle is these equilibrium points, right? Let's say this point right here. This is where mu of the solid is equal to mu of the vapor or the gas. Right? So on and so forth, right? We could have solid or liquid, we could have liquid or vapor, or we could have a triple point right here where the mu values of solid and liquid and vapor are all equal, right? They're all equal. Now, at some point, a lot of gases will reach a critical point up here, right? And above this critical point, things like, so basically what you would see here in this critical point. Let me see if I have a thing for it. Yes, exactly. Right. So for a critical point, here's what happens, right? Normally we would have gas, right? We'd have some vapor above, and some liquid below. Like when we get up to the critical point, right, the density of the vapor increases, the density of the liquid slightly decreases, and then there comes a stage at which the two densities are equal and the interface between the fluids disappears. This is the critical point, right? So again, there's not really two phases anymore, really. That's what we're looking at here. Once we reach this critical point, not everything has a critical point, but most things do. Right? So that's what a critical point is. It's not super, how do I say this? Not really all that useful, to be honest, right? Because those are usually pressures and temperatures that are much higher than what we would normally see in any normal chemical reaction. All right. Now, one thing to note here when it comes to vapor pressure, because we'll come back to it in the next section, right? Our vapor pressure has a mu value associated with it, right? Because that is a one phase, right? This is one phase, which is vapor. And then the liquid has a separate mu value, right? For the liquid or the solid, right? Now, if we're in equilibrium in a closed container, right, these have to equal each other, right? They have to equal each other. Now, if we're in an open container and the vapor pressure can escape, right, that's when we have basically constant evaporation, right? Because if the vapor pressure escapes, we have to shift the equilibrium towards making more vapor, right? If you leave a cup of water out and it's sufficiently warm enough, it'll evaporate over a long period of time, right? But if you have a sealed bottle of water, that's never going to evaporate, right? That's because it's in constant equilibrium here between the vapor and the liquid or the solid, right? If it's vapor and liquid, that's vaporization. If it's vapor and solid, that's sublimation. Right? So one of the very interesting parts of this particular section is going to be the phase rule developed by, oh, who was it? Let's see who was. Well, we'll see anyways. We'll look at it. Phase rule developed by one of our previous scientists that we've seen before in this course. Right. So this phase rule is going to give the number of parameters which can be independently changed while the numbers of phases is constant. Right. Number of parameters. So parameters are basically going to be variables like pressure, temperature, so on and so forth. Right. We'll see this. All right. So we have three different parts of our phase rule: F, P, and C. All right. So F is going to be the variance. Right. It's the number of intensive factors. Remember, intensive means it doesn't matter how much stuff we have. Like volume is not volume is an extensive factor, right? Temperature is intensive, pressure is intensive. What else would be intensive? Some other weird stuff like magnetic susceptibility, all this like dipole moment. There's lots of intensive factors, right? But pressure and temperature are the ones we're going to look at most because those are the easiest ones to change, right? And when we talk about like a vapor phase or a gas phase, pressure and temperature are going to be very important there, right? Right. Those are going to be very, very important, right? But this F is a number that can be independently changed, keyword there, without disturbing the number of phases, right? Without disturbing the number of phases. Okay. So our P is going to be the number of phases at equilibrium. That'll be pretty easy. And then C is the components of the system, right? The number of chemically independent chemical species in the system. So this independence is going to be a key thing here. And we'll go through it like this. These will become a little bit more clear as we go through the phase rule and the different diagrams. But for example, of chemically independent. All right, let's say we have a solution of NaCl. Right, so it's NaCl in water, basically. Right, Na plus and Cl minus are not fully independent of each other. Right, because if for every plus, we have to have a minus somewhere, right? There has to be some amount of charge balance. We can't create a cation and then not have a negative charge to balance it out. That's impossible, or impossible for chemistry's sakes, right? Maybe physicists can do it. I don't know. But for what we care about, it's been impossible, right? So these are not independent, right? What we're really seeing in this solution here is two independent components. One is water, H2O, and the second independent component is Na or Cl, right? They're going to be linked together, so we can count them as one component, right? That's an idea of chemically independent, right? Chemically independent. Now, this mostly applies to ions, to be honest. I think for what we'll see, it will mostly apply to ions, but just something to point out, right? So, if we consider a system with only one phase, right? Only one phase. We have a P equal to 1, right? Pressure and temperature can both be changed without changing the number of phases. Right? And so the numbers of variables we can change is going to be 2, right? Pressure and temperature, 1, 2. This is the number of phases, right? And what we see here is that in this example, it's going to be phase alpha over here. Don't worry about the letters, right? Not a big deal. Right, but if we're in only one phase, like in the middle of this phase, right, we can increase the pressure, we can change the temperature, right? No matter what direction we're going, as long as you make a somewhat small step, then we're still going to be in only phase A, right? We're still going to be in only phase A. Now, I guess the whole assumption here is that we're making a very incremental and very small step. If we're like right here, we can't make as big of a step as if we were right here, right? Well, as long as it's incrementally small, this is true. Right. So again, if we have one phase, we're going to have 2 degrees of freedom, right? We can go X or Y, basically, right? X or Y, and still remain in the same phase, right? Again, this is the number of phases that without changing the number of phases, in this case is one phase, right? No matter where we go, we're still going to have one phase. Go back. If we look at a system with 2 phases, right, pressure or temperature can be changed, right? But in this case, like for instance, on this line right here, right, where we have 2 phases, we have alpha and delta together, right? We can only change one of our 2 things, right? Because to stay on this line, if we increase the pressure, right, to stay on this line, the temperature also has to necessarily increase too, right? Again, if you change the pressure, temperature must change, and so that makes them not independent anymore, right? The basic idea, again, when you look at the graph here, or the phase diagram, it makes a lot more sense, right? If we're trying to stay on this line, if we increase or change one variable, the other one has to follow along to stay on the line, right? To keep the same number of phases, right? That's the whole point. Keep the same number of phases. If we don't care about keeping the same number of phases, then we can go up or down or left or right. It doesn't really matter, right? But to keep the same number of phases, right, they have to be connected to each other. Right? They have to be connected to each other. If we looked at a system with 3 phases, right? Here we are right in the middle where 3 phases meet, right? Neither pressure nor temperature can be changed, right? Because if you change away from this spot, then you end up in a different phase, or you end up with a different mixture of phases, right? If you change either pressure or temperature, you go away from that point, and so you're not going to be the same number of phases. All right, so in this case, the number of variables you can change is 0. Right? The number of phases you can change is 0. All right, now all of this is for a one component system. Right, this is for a one component system. We only have one component. If we have multiple components, it's going to be a little bit different. So what we can do is scale this up basically for one component, from one component to multiple components, right? So again, if you look through this, kind of puts together, the general line of thought is for a one component system, which is basically for a pure substance, right? Because if you have a pure substance, it is by definition one component, right? The degrees of freedom that we have is 3 minus the number of phases. All right, we saw that, right? If we have 3 phases, 3 minus 3 is 0. That's the exact number of degrees of freedom where we're able to move things, which is 0, right? So that's kind of rule if you work this all out, right? And now in a multi-component system, where C, which is number of components, there's going to be 3 variables, right? There's still going to be pressure and temperature, but now there's also going to be composition, right? Because if we have a multi-component system like H2O and NaCl, right? If we have more than one component, right? We can change the pressure, we can change the temperature, and we can change the composition of this mixture. So this composition is going to be a function of the mole fraction, which is chi, right? Now our mole fraction always has to add up to 1 because again, mole fraction is basically just saying of all the moles, what percentage is water, what percentage is sodium chloride, right? So it always has to add up to 100%, right? And this means the number of independent components is C minus 1. That makes sense? So let's say that we determine that the mole fraction of H2O is 0.7, right? Since if we have a 2-component system, since this is determined to be 0.7, right? The mole fraction of, we'll just do NaCl, has to be 0.3, right? If we change the fraction of water, the other part has to change also, right? And so we started with 2 components, right? But only one of them is independent, which is that H2O in this case, right? Only one of them is actually independent. The other one, by mathematical definition, has to change whenever you change the other one. If we had 3 phases, right, we could do, let's see, like this. Let's say we did the same thing, and then we added a little bit of, oh, I don't know. Let's just do nitrogen gas, something like that, right? If I change the amount of H2O, right, either NaCl or into could change, right? I could change the HCl, I could change this one, I could change this one, and then only the very final one would have to be like set in stone mathematically. Right. So again, number of independent components is going to be C minus 1. Each phase can have its own composition. So we have all these different phases, right? They can all have their different compositions. They don't necessarily have to have the same mole fractions of everything, right? If we had, for instance, a phase diagram of this mixture here with water and sodium chloride, right? Well, the vapor phase of this is just going to be pure water, right? Because we're not going to have, we have salt water basically, right? If you vaporize it, it's going to be pure water for the vapor phase. And that's only going to have one component, right? Only going to have one component, right? And again, each phase has its own composition. For the total number of compositional variables is P times C minus 1, right? And number of independent components times the number of phases. And thus, the total number of intensive variables is going to be, all right, this is all the components. This is for all the different components, the composition, plus 2 for pressure and temperature, basically, right? Go back. And this is P times C minus 1 is all the composition. And then the plus 2 refers to pressure and temperature. Right? That refers to pressure and temperature. Again, those are the three things that we can move, right? Three variables: pressure, temperature, composition. We see it right there. It's just that composition is a little bit more mathematical than the other two, which are just straight up numbers, right? So again, as we know for sure, at equilibrium, the chemical potential mu is going to be equal in every single phase, right? Every phase that connects, they have to be equal, right? There are going to be P minus 1 equations per component to be satisfied. So the total would be C times P minus 1. So here's a little mathy math stuff to kind of go back and consider. All right, so if we are on this line right here, right, where we have these two phases interacting, we'll do phase alpha and phase delta, right? The mu value of phase alpha is going to be a function of pressure and temperature, right? And that's going to have to equal the mu value of phase delta, also going to be a function of pressure and temperature, right? Now, mathematically, there's only going to be a certain number of solutions that satisfy both of these functions, right? Only a certain number of solutions are gonna satisfy both of these functions. Let me see how the book describes it. It'll be a good way of describing it. Let me see. Right. Right. This equation relates pressure and temperature. When the pressure changes, the changes in the chemical potentials are different in general. So in order to keep them equal, temperature must change for two, right? Yes. Right. If we go to a three-component system like this, right? If we look again at this point here, right? Mu of, that's a terrible mu. Mu of alpha has its pressure and temperature, function of pressure and temperature. That has to equal mu of delta with its pressure and temperature. And it has to equal the mu of beta, which has its pressure and temperature. Right? So all different. Right? It says the three phases of one component system are in mutual equilibrium. The chemical potentials of all three phases must be equal. Right? And this relation is actually two equations, which is going to be alpha equals delta, right? And delta equals beta, right? In which there are two variables, pressure and temperature. All right, with two equations for two unknowns, there's a single solution, right, that is going to make them all work. And that's algebra. Like, I'm not going to work that particular thing out, but that's algebra, basically. All right, so when we get down here, if there's two phases, right, we only have one solution, right? If there's three phases, there is two solutions, right? So again, P minus 1 equations, I'm saying it wrong. There's P minus 1 equations to be satisfied, right? So that limits our degrees of freedom, right? Basically, if we have three phases, we need to satisfy two equations or two variables, I should say. And this limits the degrees of freedom, right? Right? Because we can only, like, if we have two things to solve for, they're not independent anymore, basically. Okay. Anyways, so the total would be the number of components times P minus 1. That's how much is being limited. All right. So our total degrees of freedom is going to be, right, this is the composition, pressure and temperature, and then we have to subtract out all of the like the non-truly independent portion. I guess we call it that. All right. C times P minus 1. All right. But if we simplify all of that, right, it comes out much, much simpler and nicer to being F, the degrees of freedom, equals C minus P plus 2. And if we go back, again, if we look at our, if this, right, if C is equal to 1, right, this rearranges to what we saw before. The 3 minus P, right? If C is equal to 1, that can rearrange to 3 minus P, right? Or negative P plus 3 if you want to be like that, right? What we saw before. But this is a general for a multi-component system, or really for any component system, especially for a multi-component system. All right, if we wanted to use this, right, the maximum number of phases that can be in mutual equilibrium in a four-component system, right? So we have 4 components. Right? If we're in mutual equilibrium, right, then they'll have to be together, right, in the same place. All right. So for any of these phases, right, the lowest possible value of our degrees of freedom is going to be 0. All right, we can't have -1 degrees of freedom. That doesn't make any sense, right? So the maximum number of phases is going to be with respect to the lowest degrees of freedom, right? So if F equals C, go back. There you go. F equals C minus P plus 2. Minus P plus 2, right? Well, if F is 0, right, the minimum amount of freedom means the maximum amount of phases. Our components, there's 4 components in our system. Right. Put it all together. What do we get? 0 equals 6 minus P. That means we can have a maximum of 6 phases in a 4-component system. And that's basically all we can do about it. Right? That's basically all we can do in this phase diagram thing. It's really more about looking at phase diagrams. Right? There's not really a whole lot of math in this. I mean, if you could do this little simple addition and subtraction, that's pretty good, right? But that's basically all we can do with it. Now, if we look at some different phase diagrams for different common chemicals, common molecules, right? Here's an example of one for carbon dioxide, right? One for carbon dioxide. And if you say, note the break here in the vertical scale, right, it gets much more bigger. All right. So in this case, if we look at carbon dioxide, one thing you will notice is that it has a triple point, which is not unreasonable. Right. Temperature of 216.8 Kelvin, which is, what is that, negative 50 degrees about, right? Yeah, 60 degrees, something like that, right? And then a pressure of 5.1 atmospheres, which is not all that crazy. Right? But if you look under normal circumstances, like if here's normal temperature, 298 room temperature, right? At 298 and 1 atmosphere, right? We would get gaseous carbon dioxide, which is duh, of course, right? Right. But what you also notice is that at this temperature, at room temperature, basically, there's never a way to get solid carbon dioxide. Right? There's never a way to get carbon dioxide. As it says, right? There's never a way to get solid carbon dioxide at this temperature. And if you look at normal pressure, right, what you can also see is that at normal pressure, there's no possible way to get liquid carbon dioxide at normal pressure. So it takes a lot of wrangling in order to make all this stuff get where we want it, right? And so if you get something like the solid form, which is dry ice, right? It's called dry ice because, right, it's cold, the temperature is cold, right? It's at 1 atmosphere. When it warms up, it transitions, go back. into the vapor state and not into the liquid state, right? An ice cube would go from ice to water, right? Solid to liquid. But this dry ice, because the pressure is not high enough, right, can only go from solid to gas, which is sublimation. All right, sublimation. So that's how it is. Now, if we look at water, right, water is kind of all over the place. All right, this is actually going to be more common than you might think. All right, so we have the same sort of, if you look at like this part below, it's the same sort of diagram, isn't it? Right, we have solid, we have liquid, and we have vapor. All right, the crazy part is going to be all the different phases of solid here. Right, all the different phases of solid. Right, so we have like ice 1, ice 2, ice 3, so on and so forth. Right. Right. Solid phase ice is ordinary ice. Now, the difference between all these different phases is going to be the crystalline shape of the structure, right? So water, or ice, as you may know, tends to have a very hexagonal shape, right? Because of the hydrogen bonds, it has a very hexagonal shape, right? That's why all of our snowflakes have kind of like a hexagonal heart and kind of grow out from there, right? But as we apply increasing pressure, like if you look at some of these pressures, let's see, this is in pascals, right? So we are living, we're like right here, or something like that's where we live, right? Well, if you go, I don't know, to 1,000 ATM or something like that, right? You can literally think of the pressure like just kind of smashing this kind of a crystal structure and deforming it a little bit, right? So that's what tends to happen a lot, is that as we increase the pressure to more and more and more, like when you get up here 10 to the 12th pascals, that's, oh, what does that be? Like millions of ATM, right? Million atmospheres or millions of bars. That's a lot of pressure, right? Of course, we're going to start deforming these things quite a bit, right? Especially for a structure like water, where all of this, like the hexagonal and regular ice, is based off of the like maximizing the energy of the hydrogen bonds, basically, right? And if we increase the pressure, that may not be the truest thing anymore, right? Again, we'll talk about this on the next section, right? But we've increased the pressure. All of these have their different values of mu, right? And depending on which value of mu is the lowest at any given pressure or temperature, right? That's the phase that becomes dominant, or the phase that this component will change into, right? So if we look here, very interesting triple point on water. I don't know exactly, probably like 298, something like that. And 10 to the third pascals, which is going to be less than atmospheric pressure, right? So you can't have solid, liquid, and gas water all at the same time, but you have to actually decrease the pressure in order to do that. And then finally, we have this very interesting one, which is going to be for helium, right? For helium. Now, there's different types of helium, right? There's helium, excuse me, 3 and helium-4. Helium-4 is the normal one, right? It's a very normal one. Helium-3 is a little bit kind of all over the place, right? But this example here is helium-4, right? And we see lots of crazy sort of stuff here, right? So we have 2 different liquid phases in helium. Okay, we have helium-2, which is a superfluid. So a superfluid is a liquid that flows without resistance, right? It's a liquid that flows without resistance, right? Yeah, without viscosity. That's a better way of saying it, right? That's the difference between a regular liquid and a superfluid, is it flows without viscosity, which is kind of interesting here, right? And look at the temperatures, so very low, right? So very low, right? But if a pressure of over 20 bar has to be exerted before solid helium can be obtained, right? And we also have 2 different phases of solid here. We have this body-centered cube and this hexagonal closed packing, right? Different crystal structure types, basically, that happen in here, right? But again, this is a very interesting, rare example of having two different liquid phases, right? Again, if you think about it, because the liquid fits, all the molecules can move around a little bit, and it fits the shape of its container, basically, right? We would expect to have only one liquid phase because it can just be whatever configuration it needs to be, right? Same thing with gas, right? Gas molecules are flying all over the place. They're very random. There's not really going to be a different compositions of gas, of random gas molecules, right? So this is an interesting little portion about helium being just very, very different, right? Being a very, very different. But anyway, that's it for this first section, right? We'll pick up next section with thermodynamic aspects, where all the math and problems will come from, basically.